So today in Talk the Thought Process, we're going to talk through how we determine the formulas of chemical compounds by analyzing what they're made of. And we do that through a process called combustion analysis. So that's often used for organic compounds where we have carbon and hydrogen and sometimes some other elements like oxygen and nitrogen. These are very important in biological systems. And so it was determined that one way that you can find out the composition is by burning them in air, in oxygen, and you form carbon dioxide and water. And when you see how much you have, you can see where that came from and how much you end up getting. So that's how this works with the organic compounds. So here's a typical sample problem. Suppose we do combustion of a substance that contains only hydrogen and carbon, right? That's called a hydrocarbon, only hydrogen and carbon. And we burn it in an excess amount of oxygen. And from that, we get a certain amount of carbon dioxide, CO2, and water. And then from that, we want to find out the empirical formula, the molecular formula. We're also given some other information that this substance is known to have a molar mass of 86.2 grams per mole. And we can find that out from ways that are different from combustion analysis, like mass spectroscopy. That's an important way that we have for finding out, the molecular mass of organic compounds. So to do this problem, of course, we need the periodic table because we're going to be looking at mass and mole conversions to figure out what the composition of our compound is. So we'll just have that there to come back to. And so when we're given this problem, we want to think about the fact that we're burning it in air, right? So we have our hydrocarbon, and so we can kind of draw it like this. A hydrocarbon has a certain amount of carbon and a certain amount of hydrogen, right? Where these subscripts show the molar ratios of the two. We burn this in air we add oxygen gas, and we add heat, of course, fire, flame. And what we get is carbon dioxide plus water. Okay, and so when we think about these combustion reactions, what we have to do is think about, well, where does this carbon dioxide come from? And the important thing here is that the carbon in the carbon dioxide, it comes from the compound that we have, right? Because all we have in there is our compound and excess oxygen. So this comes from our unknown sample here. Right, so if we want to know how much carbon we have, we find out how much carbon dioxide we get. And all of that carbon comes from this carbon right here. Right? So if we know how much carbon we have in here, then we'll know how much carbon we started with. And so as we go back to our problem here, we have 3.447 grams of carbon dioxide that's formed in this case. So we have 3.447 grams carbon dioxide, right? That's what we're given. That's a piece of information we're given. When we burn all of this up, all of the carbon in here is converted to carbon dioxide. So what we want to find out is how much carbon do we have in there? So over here, I'll write an answer that I'm looking for, right? I'm looking for moles of carbon, right? Moles of carbon, because I'm interested in mole ratio that comes in over here. So when we're starting with grams of carbon dioxide, the first thing we want to do, of course, is to convert that to moles of carbon dioxide. And so we'll have to determine what is the molar mass of carbon dioxide so that we can make that conversion. Okay, so I'm going to just estimate a little bit that carbon has an atomic mass of about 12. And oxygen is at about 16, and there's 2 of them, which makes 32. So 1 C and 2 O's, 12 plus 32, it's about 44 grams per mole. Right, so it's about 44 grams carbon dioxide and 3.447 grams CO2. Now, if we were to be more precise here, more correct, we would want to actually use more significant figures. But I just wanted to illustrate for you the concept, right? So if we're converting grams to CO2, to moles of CO2, that's what we would do there. Right, but what we want to know is how many moles of carbon is in there, right? And so if we have moles of CO2, we need to just look at the formula there that just show that 1 mole of CO2 will have 1 mole of carbon in it, right? And so it's a simple conversion, just like the many ones that we've done in chemistry, or that we do in chemistry all the time. So here we're going to have 3.447 divided by 44 times 1 divided by 1. And so this is equal to 0.0783 moles of carbon, right? So we're thinking that through. We're getting carbon dioxide. Where does it come from? It comes from our compound. And so if we want to know how many moles of carbon we had in that starting compound, all came and was converted to the CO2. So we just do that simple conversion. Right, so likewise, we need to look at this next question. Where does the water come from? Where does the water come from, right? So again, looking at our reaction, right, the hydrogen in the water comes from the hydrogen that's here. The oxygen is going to come from the oxygen that we're putting in there, right? But the hydrogen from the water comes from the hydrogen that's in our sample. And so that's really the key thing that we need to make sure that we understand as we're doing this problem, right? So if we have our unknown compound, which is a hydrocarbon, reacted with oxygen, and we're getting carbon dioxide and water. The water is coming from the hydrogen in the hydrocarbon combining with the oxygen that we have. So that hydrogen comes from the hydrogen in the hydrogen carbon. So the hydrogen in water comes from the hydrogen in our unknown compound here with formula CXHY. Right, so how do we determine how much we have? Well, let's look at our data again. We have water, 1.647 grams of water. Okay, so if we put that here, 1.647 grams H2O, and we want to know how many moles of hydrogen is in there, right? So we simply first convert grams to moles, right? So 1 mole of water is going to be about 18 grams of hydrogen, 18 grams of water. And again, I'm rounding off a little bit, right? But we want to know how many moles of hydrogen. So we see that in every 1 mole of H2O, there's 2 moles of H. Right, so you see how nice these chemical formulas are in telling you what you've got. Right, so our moles are going to cancel, our grams are going to cancel, and so we should be able to do this here, where we have 1.647 divided by 18 times 2 equals 0.183 moles of hydrogen. Okay, so we're not done with the problem yet. We want to know what is the empirical formula of the substance. So we're looking for the values of X and Y, right? And so we saw the moles of carbon was 0.0783. Right, so we could put it here. We could put there's 0.0783, and then the moles of hydrogen is 0.183. We could do that, but we don't do that in chemistry. We don't like these big numbers here. We want to have whole numbers here that will show us the ratio. So it's a little bit easier for us to see what's the ratio. So the way we do that is we'll divide each of these by the smallest number so we can get whole numbers, right? So if we divide 0.0783 by 0.0783, we would have then carbon 1. And then if we divide, let's see, 0.183 divided by 0.0783, that comes out to 2.34 hydrogen. 2.34. Okay, so all we did was said these numbers are too big, we don't like them. We still want to show the ratio between the two numbers, so we divided the larger number by the smaller number, right? And so if we divide this one by 0.0783 and this one by the same number, then we get carbon of 1, hydrogen 2.34, right? So there what we have is little simpler numbers, but still not as simple as we want them. The ratio is still the same, right? 2.34 divided by 1 is equal to this divided by that, right? So now what we have to do is say, well, this is about 2 1/3, right? So if I multiply everything by 3, maybe I can get rid of that fraction that we have there. So let's multiply everything by 3, right? And then we would have C3 and then H, what would that be? Times 3, 7, H7, right? So we had to take a few steps to show that 0.183 to 0.0783 is the same as 7 to 3, right? So that kind of showed us that that ratio works, right? So 7 divided by 3 is 2.33, right? It's the same as 0.183 over 0.0783. So the empirical formula always has the ratio of the atoms in moles using the smallest possible whole number. That's the empirical formula that data shows us. Now, the molecular formula can sometimes be different from the empirical formula, right? So this just shows the ratio, but there can be different compounds that have the same ratio of carbon and hydrogen atoms, but actually have more atoms totally in them. So the clue we're given here is the molar mass, which is 86.2 grams per mole. 86.2 grams per mole is our molar mass. So what would be the mass of this if this were the molecule we had? Well, we would have carbon is 12 times 3 equals 36. Hydrogen is 1, and there's 7 of those, so that equals 7. So we add that up, that's about 43. Okay, so what we see is that the molecular formula, the molar mass is 86.2. It's about twice as much, right? It's about twice as much as this mass here. So that means we again have to multiply these numbers by 2. So it's going to be C6H14, right? So we got that because 1 mole is 86.2 grams, right? And 1 mole of this is 43 grams, right? So we can check ourselves, right? We have carbon is 12 times 6 is 72, and then hydrogen is 1 times 14 equals 14, and so the amount we have is about 86 grams per mole. Right, so this is the empirical formula, this is the molecular formula. So the key in doing this problem is just thinking through where does the carbon come from? It comes from our compound, right? And it shows itself to us in the form of carbon dioxide. Where does the water come from? It comes from the hydrogen in the compound, and it shows us how much hydrogen is in the compound. Once we get the moles of each, then we look for the smallest whole numbers that will express that ratio. That's our empirical formula. And when we have the molecular formula, we have to see how many of those empirical formulas will fit into this particular mass. So we look at this mass divided by that. We see 2 of those units, right, will weigh this much, 86.2. And that's how we use combustion analysis to find empirical and molecular formula.